Hello, Matthews. Gatos here. We're going to do section 9.1 today, but before we do that, we're going to review section 2.2, and I have two diploma examples to do that. So this first diploma example, I have the graph of f of x, which is a quadratic function, and I want to know things about the graph of the square root of f of x, specifically the domain and the invariant points. So if we look at this graph here, the very first thing that I know is that the graph of root f of x will not exist here because you cannot take the square root of a negative y value. So the graph will not exist there. I can, however, take the square root of a positive y value. So the root function will exist here and here. So specifically, anytime x is greater than or equal to b, or on the other side, less than or equal to negative a, that will be the domain of the square root of f of x. So looking at my options, that looks like a and b. So we can knock off c and d as possibilities. The next thing I need to look at is invariant points. So when I take the square root of 0, that's still 0. When I take the square root of 1, that's still 1. So I want to look at my invariant points. So when y is 0 or when y is 1, I will have an invariant point. So I can see that there are 1, 2, 3, 4 invariant points, which would make A my answer. Okay, in this graph, we're not given the graph of f of x, we're given the graph of the square root of f of x. We're told that it has a range of 0 and 9, 9 being the maximum point. So I can imagine what the graph of f of x would look like based on this. When I take the square root of a quadratic, it doesn't change the opening. So I know that f of x is going to be a parabola that opens down. Okay? So just a very rough sketch. Since this one opens down, I know f of x will open down, and it will look something like this, for example, not drawn to scale. That would be what square root, or what f of x looks like. So what I'm going to do is I'm going to try and figure out which one of these points can't be on the original graph of f of x. So the very first place I'm going to look at is my maximum value. So the square root function has a maximum value of 9. That's after I took the square root. So before I took the square root, this graph of f of x had a maximum value of 9 squared, which is 81. So I know that no point on f of x could be above 81. So looking down here, I can see that this point right here is too big. 90 is bigger than 81. Therefore, this point cannot be on the graph of f of x. Okay, so in this lesson, we're going to do section 9.1. We're going to do this in two lessons, one for linear and the other for quadratic. So we're going to look at a rational function and how do we transform that rational function. So just to review what a rational function is the ratio of two polynomials, f of x over g of x, where g of x cannot equal 0 because division by 0 is not allowed. So we're going to look at that in a little bit more detail. Now, when I talk about transformations, I'm talking about changing a base function. And the base function in this lesson is going to be 1 over x. So I just want to get a really good idea of what the graph 1 over x looks like. So I have this table of values. I'm going to plug in values of x and figure out the value of y that goes with it. So for example, when x is negative 3, 1 over negative 3 means y is negative 0.33. I'm going to do the same thing for negative 2. So 1 over negative 2, negative 0.5, and I just keep going down the table. Right here, this one here is really interesting to me, is that it's undefined when x is 0. So I can put these points into my graph here and then graph it, and it's going to look like this. Okay, so there are two mirror images of one another with a linear graph. We're always looking for those two mirror images. Okay, So let's now talk about the domain and the range. So the very first thing that I want to note is that x cannot equal to 0. So there's actually an asymptote right there because I can't divide by 0. So what that means is that I'm never going to equal to 0. I can get close to it, but I'm never going to equal it. So my domain is the set of all x such that x cannot equal 0, but it could be any other real number. Or of course, if you wanted to write that in interval notation, it would be negative infinity up to, not including 0, or not including 0 up to and not including positive infinity. Okay, so because x cannot equal to 0, that is what my domain is. If x can't be 0, that means that I do not have a y-intercept. The definition of a y-intercept is the value of y when x equals 0. Now let's talk about the range. Okay, you can see for y, it's coming down and it's curving and it looks like it's getting close to the x-axis. Same thing on the other side, it actually looks like it's getting close to the x-axis, but it actually never reaches it. So we have another asymptote that I'll draw on the graph, and that is a horizontal asymptote right there at 0. So the range for y is the set of all y such that y cannot equal 0, but is any other real number. Or if you want to use interval notation, negative infinity up to but not including 0, or not including 0 up to but not including infinity. Now, because I can't have y be 0, that means that I do not have an x-intercept. Okay, so let's review this idea of asymptotes and actually what that means. An asymptote literally translates to not meeting. So that means that the graph gets really close to it, but it never actually reaches it. So there's two types of asymptotes that we're going to be looking at. One is a vertical asymptote. Those are those vertical straight up lines that are x-equal equations. These ones here, the graph will never cross or touch it because it's based on a restriction. I'm not allowed to divide by 0, so it will never actually reach it. A horizontal asymptote runs horizontally left to right, so it is a y== equation. So this is what the ends of the graph are doing. So as I make x really, really big in the positive or really, really small in the negative, what's happening to my graph? Where is y going? Now, horizontal asymptotes are a little bit different because it can cross the horizontal asymptote. If it does, it's right in the middle of the graph. A horizontal asymptote is what happens to the ends of the graph. So this is an important thing to note. Because I can cross a horizontal asymptote, I always want to look at my graph before I state my range. So just because you have a horizontal asymptote doesn't necessarily mean that that's what the range is. So if I go back to this graph here, I can see because it doesn't cross right in this area, I know it's never going to cross. So that's kind of what I want to look at. It's just the middle of the graph. Okay, so let's look at our base function and we'll look at the vertical and horizontal asymptotes in a little bit more detail. I know I already mentioned it, but I want to in particular focus on the behavior near these asymptotes. So the base function 1 over x has a vertical asymptote at x=0. So you cannot divide by 0, the graph will never cross it. Horizontal asymptote, we said, was 0, y=0. The reason is because if I take 1 divided by any number at all, positive, negative, big, small, it's never going to equal 0. It can get really close to 0, but it's never going to truly equal 0. So that's why the ends of the graph are getting really close to this horizontal asymptote. Now let's talk about the behavior. When we talk about behavior, I have a little note down here. When I talk about the behavior of the graph, I'm talking about y. Whenever we talk about functions, we're talking about y. It's all about y. So it's as x approaches a certain number, where is y going? So let's talk about vertical asymptote. As x approaches the vertical asymptote, what is happening to y? So let's look at this graph here. So I'm going to look at as x approaches the vertical asymptote. So vertical asymptote in red here. So look, as x gets really, really, really close to the vertical asymptote there, y is going to positive infinity. On this side over here, as x gets really, really close to the vertical asymptote, y goes down to negative infinity. So as x approaches the vertical asymptote from either side, y approaches positive and negative infinity. Now let's look at the end behavior. End behavior, the ends of the graph, means as x gets really, really big on both sides, where is y going? Remember, behavior is always about the y. So this time I'm going to get x to be really, really big. So as I'm getting it bigger and bigger and bigger and bigger and bigger, you can see the graph is approaching the horizontal asymptote. On the other side, as x gets really small, so as I'm getting x smaller and smaller and smaller and smaller and smaller, you can see that y also approaching the horizontal asymptote. So that's what the end behavior is, which is the definition of a horizontal asymptote. As x gets big positive or small negative, y will approach the horizontal asymptote. Okay, so here I have a graph of a function that has been transformed from 1 over x. Okay, it's a rational function, and based on this graph, I want to identify some important parts. Okay, so let's talk about the vertical asymptote. So here in the purple here, I can see this straight up and down line at 1, 2, 3, 4. I have a vertical asymptote at x equal to 4. So the domain is based on this vertical asymptote. So a vertical asymptote is an equation, not an inequation. The domain is the inequation. X can't equal 4, but is still any other real number. So the behavior near the non-permissible value. So let's look at as I get closer to the non-permissible value. So on this side here, as I get closer and closer and closer to the non-permissible value, y is going to positive infinity. On this side, as I get closer and closer and closer to the vertical asymptote, y is approaching negative infinity. So in this case here, it's approaching positive and negative infinity. Okay, let's talk horizontal asymptote. So I've drawn that on the graph here, and we're going to talk about how we figure these out in a minute. So right there I can see that it's at y equals to 2. So horizontal asymptote is an equation. The range is the inequation. So you can see in the graph, and I always look in this middle section, that there is no graph crossing the horizontal asymptote there. So if it doesn't happen in the middle, it's not going to happen. So I know that the range is y can't equal 2, but is still any other real number. So let's look at our behavior as the ends of the graph get bigger. So as x gets bigger along here, you can see it's going to get closer to the horizontal asymptote. Same thing on this side here. As x gets even smaller, it's getting closer to the horizontal asymptote. So as x gets to approach positive and negative infinity, y approaches that horizontal asymptote of 2. Okay, now let's see if they have any intercepts. So I can see here a y-intercept at -0.5. So I have intercepts at -1, 0, and at 0 and -0.5. So why does this graph have an x-intercept, but the base graph 1 over x doesn't? Well, the reason is the base graph was right at 0. It was symmetrical at 0. It looked like this and this. You can see that this graph here has been shifted to the right and shifted up. So that's the reason that there is an intercept here. So important to note, this graph has intercepts because the graph has been horizontally and vertically shifted. One other thing that I want to point out is this vertical asymptote splits the graph into sections. So the vertical and horizontal asymptote splits this into 1, 2, 3, 4 sections. But there's only graph in 2 of them, and this will always be true. The graph, when it comes to rational functions, will only be in half of the sections. So you're not going to have graph in every section. So anytime you have a graph with a vertical and a horizontal asymptote, it splits it into sections. You're only going to have graph in half of those sections. Okay, so half of those sections. So I gave you the graph and you can clearly see all this information, but you're not always going to have the graph. So we're going to use this example here to build a pattern to figure out vertical asymptotes, horizontal asymptotes, x and y intercepts. So let's look at this. So that equation that we just did had a horizontal asymptote at y equal to 2. So here's my little trick for horizontal asymptotes. Horizontal asymptotes are the ratio of the leading coefficients if the numerator and the denominator have the same degree. Let's review from polynomials what a degree is. Degree is the highest exponent of x. So if I look at this, this is a linear, which is degree 1. This is also a linear, which is also degree 1. So it's the ratio of the leading coefficients. Now note I added the 1 there because if there's no number in front of a variable, there's always an invisible 1. Okay, let's use this trick to find the horizontal asymptote of this one. So again, degree is 1, degree is 1. It doesn't have to be 1, it just has to be equal. So I could have degree 2, degree 2, as long as they're equal. So since these two here are the same, the horizontal asymptote will be the ratio of the leading coefficients. So that means the horizontal asymptote is the equation 4/3. Okay, let's look at the y-intercept. Now, of course, you can always just let x be 0 and solve for y, but I just want to talk about a little trick for figuring out the y-intercept. So the graph that we did had a y-intercept at -0.5. So if we look at this here, here's my little trick for y-intercepts. It's just going to be the ratio of the constants, simply because if x is 0, we get rid of x and get rid of x because it's 0. That's all we're left with. So 2/-4 in lowest terms is -0.5. So let's use that same trick over here to figure out what the y-intercept is. So looking at this, it's the ratio of the constants. So -3/1 is just -3. So the y-intercept is at -3. Okay, let's look at the trick for the x-intercept. So this graph had an x-intercept at -1. So you can see right there, it's found by setting the numerator equal to 0. 2x plus 2 equals 0. 2x equals -2. X equals -1. Here's the reason why this trick works. If I have an x-intercept, I let y be 0 and solve for x. So if I have this equation 0 equals 2x plus 2 over x minus 4, the very first thing I'm going to do to solve this is multiply both sides by x minus 4, and then look what you have here. X minus 4 times 0 is just 0. So you're left with 0 equal to the numerator. So to save me all of those steps, I just set my numerator equal to 0. Okay, looking at this one here to find the x-intercept, I just set that equal to 0. So 4x minus 3 equals 0, which means 4x equals 3, which means x equals 3/4. So the x-intercept is going to be 3/4 and 0. Okay, let's look at the vertical asymptote. So the vertical asymptote of the graph that we looked at was at 4. So my trick for that is to look at the denominator. Vertical asymptotes are based on restrictions. You can't divide by 0. So if you have x minus 4 equal to 0, add 4 to both sides, you get your vertical asymptote of 4. So because they're based on restrictions, you always look at the denominator. So for this example here, I look at the denominator and I set it equal to 0. So solving for x, I get that my vertical asymptote is at -1/3. Okay, well these are all great tricks, but how on earth are you supposed to memorize all of these little tricks for them to actually work? So that's what I want to talk about next. Okay, so this is the way I kind of look at it. So we have this fraction ax plus b over cx plus d. So the first thing that I notice is that x is a wide number and it goes from left to right. So shaking your head from left to right like no, left to right like no. So values left and right are going to affect x. Left and right are going to affect x. So on the top would be your x-intercepts. On the bottom would be your vertical asymptote because you can't divide by 0. Okay, let's look at y. Y is tall and y stands for yes. So imagine shaking your head up and down for yes, up and down for yes. Those up and down vertical values affect y. So that's why these are your y values that you're looking at. So the first one is horizontal asymptote. The last ones are intercepts because they don't have an x value. Okay? So that's my little trick for remembering it. So if we put this all together, this is what it will look like. So all together, x-intercepts left and right on top, vertical asymptotes left and right on bottom because I can't divide by 0. Horizontal asymptotes up and down for y. Y-intercepts up and down for y because they don't have an x. So I always go left and right for x, up and down for y, and these are the ones that help me. Vertical asymptote can't divide by 0. Y-intercept, because it has no x. The other ones, therefore, are the asymptote and the intercepts. So let's use these tricks to fill in this table. Okay, so let's start with our vertical asymptote. Vertical asymptote is based on the restriction of the denominator right there. So 5x plus 3 equal to 0. 5x equals negative 3. Divide both sides by 5, and my vertical asymptote is negative 3/5. Okay, so because it's negative 3/5, I know I have a horizontal translation because my base function had a vertical asymptote at 0, but it now has a vertical asymptote at negative 3/5. So I now know that this graph has gone 3/5 of a unit left. Okay, let's do horizontal asymptote. Horizontal asymptote is the ratio of the leading coefficients because the degree is the same. So the horizontal asymptote is 2/5. Well, that tells me I had a vertical translation because my base graph had a horizontal asymptote at 0, but it now has a horizontal asymptote at 2/5. So I know I've gone 2/5 up. Okay, let's talk about x and y intercepts. So x intercepts are found by making the numerator equal to 0 right here. So 2x minus 5 equal to 0. Which means 2x equals 5, which means x equals 5/2 as the x-intercept. And the last one that I have to do is my y-intercept, and that is the ones up and down, because it's y, that don't have an x value, negative 5/3. So y-intercept of negative 5/3. So you can see on this question here, there's a lot that I can figure out without ever putting it into my graphing calculator. I can see all the asymptotes, all the intercepts, I can even see some transformations. In terms of transformations, the only thing that I cannot see is if there was a vertical stretch. So this fraction form, really useful. Let's now look at transformed form. So over here, transformed form. So this is that back to chapter 1 form, okay? So I want to look at how have I transformed the graph 1/x to this graph here. Okay, so looking at this graph here, I can see that I have an a value of 3. An a value of 3, which tells me that I have a vertical stretch. Okay, so I have a vertical stretch about the axis, the x-axis, by a factor of 3. So remember, for stretches, we always stretch about. Remember our RISA notation? We stretch about. Okay, I can see that since a is a positive number, there is no reflection. And then lastly, I'm going to look at my translations. So here I have a +3, remember horizontal lies, and here I have a +5, remember that vertical is straight up honest. So I know that I have a horizontal translation 1 left and a vertical translation 5 units up. So let's use this now to figure out our asymptotes. So normally my vertical asymptote for my base function is at x equal to 0, but I have translated 1 unit to the left. So my new vertical So that means my domain is the set of all x such that x is not -1, but still an element of the reals. Remember, as you approach the vertical asymptote, as x approaches the vertical asymptote, and that vertical asymptote is -1, y approaches positive and negative infinity. Okay, let's talk horizontal asymptote. So normally the horizontal asymptote is at 0. But we have gone 5 units up. So my new horizontal asymptote is at 5. So I did a quick check of my graph, and it does not cross the horizontal asymptote. So I know that my range is the set of all y, such that y can't be 5, but is still an element of the reals. Now remember my end behavior, as I make x infinitely big in both directions, y always approaches the horizontal asymptote. So looking at this transformed form, just by using what we know in chapter 1, we can figure out a lot of things about this graph as well. So because each function, fraction form or transformed form, tells a lot about its graph, we need to feel comfortable switching between the two. Okay, so I want to look at how do we convert from transformed form to fraction form. Now you might ask yourself why on earth you would ever want to do that. The reason is, in fraction form, the intercepts are much easier to see. So let's practice this. I want to take this transformed form and write it in fraction form. So I'm going to do that with a common denominator. So this is over 1. So common denominator is going to be x plus 1. So to make this an x plus 1, I multiply the numerator and the denominator by x plus 1. So I have 5x plus 5. So altogether it's 5x plus 8 all over x plus 1. So now these forms are identical. 3 over x plus 1 plus 5 is the same as 5x plus 8 all over x plus 1. They are the same. So based on this fraction form, I can now see what the x and the y-intercepts are. So y-intercept, again, is the ratio of your constant terms right here. So I know that my y-intercept is at 0 and 8. My x-intercept is found by setting that equal to 0. So my x-intercept is at -8 over 5 and 0. So now that I have that, I can use all of this information to graph this function. So we have this graph here, this function here that we want to graph, 3 over x plus 1 plus 5. And I've summarized all of the information here. We're going to use that to graph. Okay, so first of all, I have a vertical asymptote at x equal to -1. I have a horizontal asymptote at 5. I have an x-intercept at -8/5 and a y-intercept at 8. Okay, that doesn't look like I have a lot of information, but I actually have enough to graph it using what I already know about rational functions. So I can see there are 1, 2, 3, 4 sections. Remember I said that the graph is only in half of them, so I see a point in this section and a point in this section, so I know that these two parts here will not have a graph. So that's useful. Now I'm going to use my end behavior to come up with the rest. So looking at my end behavior, let's use a different color. Let's use green. Okay, so I know as x gets really big, y approaches the horizontal asymptote. So I know it's going to come down like this and get close to the horizontal asymptote. For here, coming through that point, it's going to get close to the horizontal asymptote. So that kind of helps me on that point. And then let's look at the other end behavior. as x approaches the vertical asymptote, y will approach positive and negative infinity. So my vertical asymptote there in purple. So I'm going to get here, it's going to go up to positive infinity, and down here, it's going to go to negative infinity. So using all of that information, I don't even need to put this into my graphing calculator. Okay, let's look at going the other way around. Okay, so converting from fraction form to transformed form. And again, why would we want to do that? The reason is because we can see the vertical stretch and vertical reflections. Okay, so we're going to use long division to convert that. So just as a quick little review here with numbers, how we do long division, I do 19 divided by 3, which is 6 whole groups. 6 times 3 is 18. Subtract is 1, and that's my remainder. So 19 over 3 is 6 wholes and 1 out of 3 left over. So this here is my quotient, this is my remainder, this is my divisor. Let's use that now to do polynomials. So if I want to do 2x plus 2 divided by x minus 4 to write it in fraction form, I set it up like this. So I just use my first numbers. So 2x divided by x is 2. And now I multiply. 2 times x, 2 times negative 4, and I subtract. 2x take away 2x, 0. 2 take away negative 8, positive 10. That's the remainder. So what that means is that 2x plus 2 over x minus 4 is 2 wholes and 10 remainders out of x minus 4, or flipping it around, 10 over x minus 4 plus 2. Now, the reason that this is great is because now I can see this is my vertical stretch and there is no vertical reflection. So let's try that again with this one. So I want to write this in transformed form. So this is the same one that we were using before. So I want to see same kind of process that we're using before. I want to see this fraction in transformed form. So I'm going to do x plus 2 into 3x plus 7. So I do 3x divided by x is 3. 3 times x plus 3 times 2. And then I subtract. 3x take away 3x is 0. 7 take away 6 is 1. So that means that this fraction here in transformed form is 3 wholes plus 1 remainder out of the divisor. Okay, so this tells me, looking at this graph here, this is my vertical translation. This will be my horizontal translation. And here, this would be my vertical stretch or vertical reflection. And in this example, you can see I don't have any of those. So let's look at these two forms side by side just to review. Fraction form compared to transformed form. Okay, so in the fraction form, I can see my x-intercept, y-intercept, horizontal asymptote, and vertical asymptote. From the horizontal asymptote, I can figure out the vertical translation. From the vertical asymptote, I can figure out my horizontal translation. In transformed form, I can see my horizontal translation, which will then tell me what my vertical asymptote is. I can see my vertical translation, which will then tell me what my horizontal asymptote is, and I can see that there's no stretch and no reflection. So, to summarize this, vertical asymptotes based on restrictions, graphs cannot cross the vertical asymptote. Horizontal asymptotes are where the ends of the graph approach. The graph can cross the horizontal asymptote, but it will happen in the middle. To do from fraction form to transformed form, use long division, and to switch from transform to fraction form, you're going to add using a common denominator. So a student says to the teacher, to show you how well I understand fractions, I only did half my homework. I know that you are going to do all of your homework though. So let's do practice questions 1 to 4 first, and then you can move on to the textbook questions. I know this lesson was a little bit longer, but the second part to this lesson will be shorter because we've done a lot of the preliminary underground work.